Thank you very much, Detlef, and thanks a lot for the organizer in inviting me for this talk to give an overview. It's really an overview, actually, compared to the very nice talk Jan just gave. I almost have no numbers, but a lot of ideas, I hope. So what I'm trying to do is to take a look, what could be a perfect forecast? It's actually the goal, of course, all of us have, and we will take a closer look to that. Two sentences about my person. I'm a physicist. Basically, I'm running the company Overspeed with a friend since now more than 25, almost 30 years now. We are coming from the wind energy consulting. That's our base work and the core of the company. But today we are doing more and more forecasting, and these are the four fields we are working. As I mentioned, first one, wind energy consulting, then everything, assessment, wind potential, solar potential, everything which goes along with that, feasibility and that, system and software development, and of course, that's why I'm here, and what we are focusing on today definitely is wind and solar forecasting, and it's not a company presentation, can be assured. We have a system which is called Animos, and it's a little bit confusing. That's why I always give a short explanation, because Animos means a lot of things. The first was, and that was been the origin of this work, has been a leading-edge research and development process with most of the European institutions commercially and from the research field who developed together models and the system finally. And so that was the starting point of Animos, and then from that we have in the second point prediction models and modules, so implementation of models. From that a system, and that's this last one why I'm here. It was not only research, but there was a spin-off, that's what I am leading, which offers commercial wind and solar predictions. If I say we, then it's not only Overspeed, but it's a number of companies and institutions in Europe, and at least 2 or 3 Oldenburg University, Paris, École des Mines, Paris Tech were mentioned already in Jan's talk, so it's wind and solar definitely in total. So I can say we have so much gigawatts we are predicting worldwide with our partners in these and these countries, but I got a much nicer opportunity to show what we think where we are standing, because we got this nice slide yesterday in Simon's presentation from the IEA about the phases in different countries. From the green one, phase 1, phase 2, which are the economies with high penetration in wind, but we are still doing okay. Then the red ones, from a medical point of view, they should see a doctor, let's say, so they need some support to get to remain a stable system. And then the blue ones, who are the emergency room candidates, let's say, so who have really daily doing a lot of struggling to get their system stable. On the list it has been IE, so Ireland in Europe, Australia, and in particular Southern Australia and Denmark. And I'm happy that all these 3 are counting on our predictions. In Denmark, of course, traditionally, because it's one of the first high penetration countries, we are doing predictions. Since many years, Australia, we are the reference prediction for the Australian energy market. And in Ireland, we are one of 2 prediction suppliers for the Irish grid operators, Ireland and Republic of Ireland and Northern Ireland. Okay, so what will I talk about today, apart from this now stop of advertising? 4 points. Wind power prediction, what are the principles? Very shortly, just to give the framework, and I can go along this path. And secondly, the perfect prediction models. Second point will be, main point will be, I'm looking into the power data, because it's an issue which is getting, it's a field which is getting more and more an issue. And finally, of course, I will draw some conclusions. So if you take a look at wind power predictions, then of course, we have some wind farms operating, then we are now, and now we want to know about the future. So, and future can mean a lot of things, can mean next 5 minutes, can mean 2 hours, can mean day ahead. We heard about a week a week ahead, which would be required for Tamil Nadu yesterday, yeah, to fire up coal power plants which are under maintenance if something is happening in the next 5 days. So that depends much on the application, of course, what makes sense. And then we have the future reality, which unfortunately we don't know at the moment, but it will match the predictions, and sometimes it won't. It won't. That's how it is with predictions. One of our customers, when the control room complains, oh, we got again a wrong predictions, and it says, of course, it's wrong. It's a prediction. And that's how it is. Yeah, we are wrong and we are right, and hopefully, and that's what we are all struggling for. We are, in most cases, we are right, but there always will be wrong cases. And Jan already showed that. Of course, today we are also trying to give an uncertainty. So we are not only giving a prediction, but we're saying how accurate is it? How accurate could it be in this specific weather situation, in this specific power range, and. Okay, so that's our goal finally, in principle. So the question is, how could we do it perfect? And we have a lot of ingredients going into that. From left to right, we have the NWP data, which is very important. It's not a focus of this talk, but I give some remarks at the end. We have historical power, which was measured and which we got in our databases. We have then a number of prediction models, and we have the online power, which we get currently from the farm. And all this together we put into a prediction system, and the question is, how can we do that in an optimum way? And I'm always trying to find a picture to figure out how can this be done in a good way, and this time I will try to take an analogy with cooking. So if one is trying to make a curry, and if he's Indian or she is Indian, whoever is doing it, then he will definitely use a lot of chili. Yeah? If I'm doing it, it more looks like that. Yeah? I love Indian food, but sometimes a little bit hot to me. Actually, I'm working a lot in Chennai at the moment, in Dr. Katya's Institute Nive. And if you're going there, then it more looks like that. You know? And it's the same with predictions. Yeah? It depends for whom you are cooking. It depends what you want to reach. That makes up your ingredients you are using. Yeah? Taking a look at the applications. Of course, we have grid and system operations. That's the obvious application we are using at the moment. So power plant dispatching, reserve planning, congestion management, extreme event handling. By the way, Jan mentioned that already. Not only the methods are deriving from the application, but also the error measures. Yeah? What is an error for me? Yeah? It could be, if I'm interested in extremes, then it's a wrong ramp, with a wrong phase, for example, wrong timing. If it's balancing markets, and it could be the RMSE, but it also could be the absolute error, because maybe it's not, extreme deviations are not too expensive to me, so I don't care about the extreme deviations. So also the error measures depend on the application very much. And of course we have other applications which are not so obvious, but today getting in many countries standard energy trading. Of course, all short-term markets depend on short-term predictions of wind power and solar power, of course, naturally. The load predictions, which is coming up more and more, mainly with rooftop solar, because the rooftop solar is finally messing up your load data which you're measuring at the households. And O&M optimization for wind and solar also is something which is used more and more. And of course, all that, we have heard a lot about it, and I think that were very, very, very nice talks yesterday. It all depends on rules and regulations, because the rules and regulations tell you as a forecaster what you can do, which information you have, what qualities the data have, and. So that's extremely important, this level. Okay, so there's a different kinds of ingredients, and now looking a little bit more into prediction models. So input is clear, NWP data, online power, and historical power, and then we get the predictions idealized, or this is a real-world prediction, as I said, with uncertainty bands depending on the weather situation and other stuff. Just to get an overview again. So if you take a look at the modeling, then first of all, we have two big kinds of models. One are what I call a physicist, because in physical modeling, or parametric modeling or whatever, or statistical modeling, which is mainly based on statistical methods and doesn't take too much knowledge about the real world into account. And today from the behavior of different prediction models, prediction systems, commercial prediction, and a lot of research is rather clear. In wind energy, it's obvious that it makes sense to use a combination of physical modeling and statistical modeling. I will give an example in a second why statistical modeling is very important, but also sometimes a little bit critical. From experience, as I said, always a combination of physical modeling and statistical modeling makes sense. In some cases, some application in solar, it could be a little bit different. Why could statistical models sometimes have problems? The main reason for that is a real strong nonlinear behavior of the power curve, which you can see on the right side on the screen, and that for purely statistical modeling may cause some problems. Finally, the message is like in the evaluation of wind resource and solar resource, you try to use all knowledge you have about the system to make a good prediction. Don't trust just on one model, for example. A note on machine learning, because that's extremely popular at the moment. It has a very, very big advantage. You don't have to know a lot about the system, but you put in your data as much as you can, and then you get out some results, and there's a lot of progress in that. Many companies worldwide are pushing these technologies, and it could be a great asset for some applications, in particular for the very short term, and for post-processing of predictions. The issue with machine learning is that it's really good if you have big amounts of data, and unfortunately we don't have that in most applications. When we talk about wind and solar predictions, we just have a little bit less than 10,000 hours per year, and that's for more or less the portfolios which we must work. And we have this nonlinear behavior of the power curve, and we have extreme events, which maybe, if we are talking about storms, maybe occur 5 times a year or 10 times a year. And that's always a big threat for machine learning in general, the extreme situations which you don't learn, and which then can really cause surprises in the output of the different models. So that's definitely a risk assigned to machine learning. So I think it has a good slot where it could help predictions, but as the only method, I think it's for wind energy, it's too risky. For solar energy, I'm not decided yet, to be honest. Okay, so if we take a look at the time domain, still about the modeling, if we start with very, very short-term predictions, 5 minutes for Australia, for example, and for parts of the US, and then going down the line down to days ahead and up to 10 days, theoretically, then on the very left, we see that the statistical models definitely have their domain in the very short term, and there they are very, very valuable for the next minutes and maybe an hour or so. And then if it comes to more than hours as a prediction horizon, then we always would use physical statistical modeling and, of course, an input from the numerical weather predictions, from the weather services. In parallel, I said we always will have some statistical modeling in our model chain, maybe as post-processor, and of course we expect that they are auto-adaptive, so that they are getting better over time without manual interactions. That helps us a lot to keep our O&M costs low, of course, and it gives us better predictions. One example from one model from our partner in Denmark, we have the forecasting error, single farm, real-world data. We have the forecasting error on the y-axis and the time on the x-axis in quarters, so it's 3 months. Each is 3 months, quarter 1, 2, and 3. And we see quite nicely, we start with a new farm which was newly built. We don't have historic data, so we made a physical guess what we think what could be the outcome of this farm, and then we look at the error, which is in the order of magnitude of, let's say for the best model, 10%, and then over time, just by adding new, good real-world data, production data, the models are adapting themselves and then going down. If you look at the best model, from about 10% down to 6%. So that's a nice contribution of statistical modeling, and that helps a lot, again, as I said, to get good predictions with limited O&M costs. And again, in our system, for example, behind these are different NWP inputs going into the system. Behind that, there again would be a statistical models which would combine the different data flows, again, in a prediction which is still better than the best one of these four. Okay. It's hard to see here. Yeah. So the second point, first point was modeling. Second, power data, which seems to be trivial from the very first point of view, but in practice, and it's getting more and more complicated and more and more challenge to work with pardon me. So it's better to work with online power data, and I will show why. Theoretically, of course, it should be ideal. I get directly from the wind farm operator, I get a real-time signal, let's say, like from a conventional from a conventional power station. Every 4 seconds, I get a power signal, and I'm very happy with that for my predictions. But unfortunately, that's not the situation in the real world. And today, data is more and more disturbed by turbine failures. Since ever, of course, the availability of wind and solar is not 100%, and it depends on the country in which you are doing predictions, how high or low this availability of the turbines can be. That's rather clear. Secondly, of course, SCADA feeds are breaking, or they are badly maintained, and they don't come for days or weeks or whatever. So the data could be bad, or the connection could be broken. Actually, of course, bad data which is not signed as bad is a bigger challenge actually for systems, which makes predictions. So that's a data flow thing. Then, of course, also the substation doesn't have an availability of 100%. That's very different from country to country. The same is true for the grid availability, which in some areas of India could be quite low. Grid congestions, of course, and congestion management is very important, and system services. So, for example, what we heard yesterday, approaches to providing chiller services with wind and solar could, of course, also have an influence on the data. If we take a look from the practical point of view, so the blue one upper curve here is the ideal power output from the wind farm following the wind. Then the pink one would show the limited turbine availability, so something between 80 and 97%, as I said, depending on turbine type and everything. And then, unfortunately, in many cases, in particular in high penetration situations, we have grid curtailment, which is an additional influence on the data. So the data is disturbed, and somehow we must deal with it. And there are upscaling models to deal with that, presuming that you have detected the influence of availability and so on. Sometimes it's not so easy to know, is the turbine going wrong, or is it curtailment or whatever. Okay, so we need power, definitely, that's clear. And if possible, then we need turbine availability, set points for curtailment, and an idea about the data quality. The last one, in most cases, is not provided by the customers. We use wind speed measurements for upscaling. They could help a lot, not directly for the prediction process, but for correcting data. Okay, so I will skip that and summarize. So we got 4 inputs, NWP, historical and online power, these are 2, and the prediction models themselves. And we also could talk a lot about NWP data. And of course, if you make a system, it looks much more complicated than the 3 boxes at the very beginning. Yeah, but you have a lot of small boxes for quality management, for reporting, for making the system reliable and stable. And that's what I think are my messages. First of all, prediction systems must be robust and flexible. You can do a lot of model development at your desk, but in the real world, data is disturbed by everything, or data is missing, or whatever. And there's a lot of work apart from modeling, which must make your system robust. This also means, of course, the models must be robust and flexible, and data quality management is a very essential issue, so you know about the data and the basis of your prediction data. And to make that happen and make your life as a prediction provider as easy as possible, we need well-designed regulations and rules. And fortunately, yesterday there were a lot of discussions about it already, and there are some nice rules in place already in India. And it's like in all countries, that they are in place on some level doesn't mean that people follow it. So it's very important that they are enforced, and that finally the data which you get from the real wind farm is in line with the fine regulations which were worked out a little bit earlier. And so about the perfect predictions, it was a starting point in order to get in a perfect prediction. We definitely use more than one NWP, could be another talk. It's very important to include local models, because the local weather services know much more about the situation in this country and in different regions than you ever can do. So try to include local models in addition to the models which are used anyway. Best measurements data we can get, of course, it's clear, and the regulations should give a nice framework for that. And excellent predictions, finally, need good models, definitely, but also excellent data sources. That's the key for everything. So thank you very much.
Yeah, thanks a lot, Igor, for your report out of practice. So are there any questions? Yeah, please. Could you wait for the mic, please?
Sorry. Thank you. Yeah, how much error is due to the numerical model, atmospheric model, or how much due to the power model?
Sorry, can you repeat, please?
How much error is due to the numerical weather prediction model, and how much due to the power model in total predictions?
I don't think that we can distinguish that, if you're honest, because finally, let's say day ahead, for day ahead forecasting, the NWP is the most important input, and then we are doing the best what we can with the power data we have. So I would say the spread between different NWP model inputs is in the order of magnitude 30%, I would say, difference between different models. A good model and an average model. There are no really bad models on the market at the moment, I would say. Yeah. And then, with bad production data, of course, you can make it totally wrong. Yeah. So it's very hard to distinguish between them. It's easier in solar forecasting, because it's more linear, and you can say I use solar measurements. For winds, actually to evaluate NWP models with wind speed data is extremely difficult, because you learn very little for the power prediction due to this nonlinear behavior of the power curves. That's the main problem. Yeah, for solar, it's a little bit easier. You can look at irradiation data. For looking for wind data, it's important to evaluate weather models, but it doesn't give a good indication for the power error. Finally, unfortunately.
Yeah, my reason of asking: suppose we say weather model is 100% accurate, even then we'll have how much error in the overall predictions? 10%, 20%.
No, the problem is, what does it mean? It's 100% accurate. Accurate compared to what? That's exactly the problem.
No. Prediction we can always compare with the actual value. That we can say today's weather prediction it is 100% accurate. We can say, suppose.
For what?
For tomorrow's wind.
For the wind speed at the site at hub height, let's say.
Yeah.
Then the power model makes maybe another 5% or something like that.
Yeah. Thank you.
Thanks.
Yeah, please.
Wind and solar both have prediction model. Which is an easier or more complex? And what are the chances of more success of a model? Whether solar can be predicted more accurately or wind can be predicted more accurately?
That's a good question. For solar, you have the problems that you have clouds. Without clouds, we all would be very happy, concerning predictions, with respect to predictions. For a single solar farm, I guess it's definitely more difficult to predict solar. For wind, you have, on the other hand, you have a lot of local influences which you don't have for solar, or which are smaller for solar, I should say. So it really, again, depends. In general, solar could be a little bit easier if we are not talking about a single small installation, but about a bigger area, I would say. But that's something I guess Detlef and Jan also can comment on. That's my opinion.
Then let's start on the left side, yeah?
Sir, the errors you have mentioned, that is with respect to install capacity or average generation during the day? Errors in the 17th guide you have mentioned.
Sorry, I couldn't understand.
Errors. The errors that you have mentioned in the 17th guide, that is with respect to what? Install capacity? What is the denominator you are considering?
Sir?
Denominator what you are considered, sir? Install capacity or average generation? Sir, error is actually forecast minus actual divided by some factor. That is install capacity or average generation. Which one you have considered?
Yeah, install capacity is a standard which is used everywhere, but finally it's something you can calculate from one as well. But this worldwide standard is definitely installed.
Install capacity.
Installed capacity.
No, normally, sir, I will add to that. Normally, the installed capacity is taken, but we take that day how many machines were operational on that day.
Yeah.
So we will divide by the actual, the machines which are generating that day. Yeah. So that is the, CRC norms.
Capacity, yes. Okay, sir.
That is the norms in India from Central Electricity Regulatory Commissions.
Yeah.
Please.
Sorry.
I forgot him.
Felix Hübner from GIZ. In India, we do have a very good insulation for PV installations, and in winter we also have tremendous problems with air pollution, which is something that is not really covered by standard models.
Yep.
I have a question for that, because there were several sources for air pollution, and just to give you an impression, air pollution can mean that you hardly see the other side of the road.
Yep.
And that can be caused by entirely external factors of weathers, like burning of firecrackers, burning of fields.
Yeah.
And it can be reinforced by weather factors like low pressure, falling temperatures, and so on. How can you incorporate that? Because I would guess that PV production is affected at least by 20–30%.
Yeah, that's a very important point. First of all, I'm quite happy about that question because it gives us the possibility to relate to a project which has been on the last slide and I skipped by GIZ in the Institute of Dr. Girda and Dr. Katyal, where exactly a team is digging into that, an Indian team which is trained by a lot of people from Germany and India. Also Detlef Heinemann and me are giving trainings there to get a better idea how to model that, to finally get a solar prediction model which is specific for India and which takes into account air pollution and aerosols and everything. If it's about fog, actually it's very, very difficult. It's also something which is an issue in Germany. And you try to get an idea from satellite pictures about that, if it's really fog or if it's something different. But it's still very hard to do that. So that's definitely some current research, and that's, as I said, it's also ongoing here in India, fortunately. So that's very nice.
Hello, Jan Gemmers from the Energy Research Center of Lower Saxony. You talked about a perfect prediction. In your opinion, what is a perfect prediction? Given your experience, at what point are you satisfied? At what accuracy and what error?
Not at all. First of all, we're never satisfied, and secondly, it depends on the application. Yeah? And that's exactly the message I wanted to give, and I think also Jan in this first talk gave it. It depends on which time scale do I look at. Do I look at averages? Do I look at ramps? So there is no perfect prediction in general, but it really depends, and it's very important. Also, through the whole chain, from the regulators down to the one who is doing the prediction and the one who is using the prediction in the control centers, what is the business process behind that? What causes me problems and what it doesn't? So that's when we are using commercial prediction or selling commercial predictions, We are digging very deep with our customers into that because they, in general, we have a tender and they give you ideas what they need the predictions for and the business behind that. And then first we discuss the business process because in most cases what the people do in the control room is something different. What the management thinks is a business process behind that. So it really makes sense to go deep and deep and deep into the usage of the prediction and then backward and find the right prediction approaches.
And what would you say for an owner of a wind farm? What accuracy does he want from you when he asks you to calculate something for him?
What he wants, if we're talking about India, of course, he wants to pay a penalty which is as low as possible. Yeah, and that's the margin which is given by the regulator finally. And we made some model calculations for different wind farms. It depends again on the local influences on the wind farms, but you can get definitely better than 90% of the time where you don't pay any penalties. Very, very, very roughly.
Thank you.
We have a question in the back and then in the front. First there.
I'm Sanjay Mathur from Rajasthan. Just to supplement the person from GIZ, we have got a phenomena in Rajasthan wherein shifting sand dunes take place. That means a small amount of sand gets transferred through a local wind pressure to other places. It has got two effects. One is it covers the panels and also it affects the generation. So how do you factor in this particular phenomena, which is, I suppose, unique to Rajasthan?
Yeah. Yeah, I think that's very important, and I would guess that's definitely current research. And that's one reason why in the project I mentioned at NIVE, Rajasthan is one of the test regions, not only because there are a lot of installations, but also because there are special effects with aerosols and with sand and with finally then with soiling of the PV plants. So that's a special focus in this project actually.
Model of forecasting. On the average, what is the level of accuracy of forecasting you have been able to achieve? That is one question. Another question is, even during high wind time, on certain days, because of the rainy season interposing in between, suddenly 4,000 megawatt of wind comes down to zero, to 100 megawatt. How many times in a year you get that phenomena in your country, or how many times we can expect in India?
For our country, of course, or for the countries we are working, most of them are not monsoon countries, so it's more the events of positive ramps which are coming in, and that's in Germany typically 5. If we take Central Europe, the high wind areas, then about 10 or 12 extreme events, really extreme events, or something which is really a threat to the energy system, which comes order of magnitude. And what you mentioned, the negative ramps during monsoon, that's exactly one of the reasons why we think it's very important to include local meteorologists and local weather services, because we cannot know about these phenomena coming from Europe. We don't have these. Yeah, we don't have experience with that, and that's very natural for me to include local knowledge to get all situations which give a threat to the energy system. A good modeling, let's say. And the first question is very difficult to talk about prediction accuracy, because it depends on the size of the areas, the time resolution, and. That's why I give always.
Say, for example, for a whole state.
Exactly. That's like why I'm
8,000 megawatt of wind installations.
That's why I'm always giving the best number I can give. Whole of Germany, day ahead, 3.5% RMSE.
Very good, very good.
It's a process of 15 years of improvement, yeah, I should mention. And also improvement, if I say improvement, not only what we are doing, but also about the data flows, data quality. So that was, I think there was a big change in improving the data flows. And that made it from 4.2 to 3.5 or something like that. Yeah, so it's so important.
Well, so one last question for the keynote speakers, then we will move on to the technical speakers. Okay, thank you very much, Igor.